In this chapter, we're going to start looking at applications of derivatives. In this lesson, we will be continuing our look at related rates.
Okay, hi everybody. Let's just keep going with some more related rates. So here we go. A trough is in the shape of a rectangular prism. It is 20 feet long, 2 feet wide, and 3 feet deep. If water flows into the trough at 3 feet cubed per minute. Okay, so again, what do we know? Well, we know that volume, okay, is going to be changing at 3 feet cubed per minute. Okay, so that's given to us right there in the problem. Now the question is, how fast is the depth of the water changing? Okay, so we are looking for dH by dt, the height of the water. We don't know what that is. We are given one little bit of information though, when it is 1 foot deep. So h is going to be equal to 1, okay, 1 foot, at the moment that we're interested in. Now the other thing that we know is the shape of this trough. So it's a rectangular prism, so it's looking something like this, right? And so water is flowing in. We already know the rate at which it's flowing in here. Now, when we think about the volume of water that's in there, see, it's an interesting thing with this shape right here, because we know that it's 20 feet long. Okay, so 20 feet, 2 feet wide, and 3 feet deep. So, but when the water goes in, it is going to spread out. It's basically going to cover the entire bottom there. So when we're asked to figure out the rate at which the height of the water is increasing, now bear in mind that we're talking about the volume of water compared to the height of the water. So when we talk about the volume of the water there, what we've got here is you've got this little bit of water that's sitting in this trough, right? Where this is the height. It's not 3 feet is the height, but the width is 2 feet and the length is 20 feet. So if you've got length, width, height here for your volume, well, your length is 20, your width is 2. Okay, h is the variable here. And I don't have to do anything else to make it the variable, it just is the variable. So my volume here is going to be 40 times, whoops, used the wrong variable there, 40 times the height. Just change that L. Takes a little bit of work, but the L is now an h. Okay? Now, I've got a relationship between volume and height. It's a very straightforward thing to take the derivative with respect to time. When we take the derivative of the right-hand side, you're going to get 40 dH by dt. Okay? Now, what's interesting about this is notice that when we took the derivative, I no longer have the variable h in there. So the fact that the height was 1, that's a bit of a red herring. That has nothing to do with the actual problem here. That actually makes a lot of sense. It doesn't really matter how deep the water is in a situation like this. The water is going to rise at the same rate. As long as you keep pumping in the water at a constant rate, it's going to rise at the same rate. And that's because the dimensions of the shape here, in terms of the length and the width here, doesn't change. Okay? And so now we know that this is going to be 3 dH by dt, and so then we divide and we get that it's going to go up by 3/40ths of a foot per minute. Actually, I'll do it like this, 3/40ths of a foot per minute, and that is my dH by dt. Okay. So now in this question we're going to take a look at the ladder problem. And these ladder problems, these are classic calculus sorts of problems here. So a 50-foot ladder, it's a long one, leans against a large building. How fast is the top of the ladder dropping when its foot is 15 away from the wall, moving out at 3 feet per second? Okay, let's take a quick look at this. So what do we know here? Okay, well, first of all, we know that we've got this ladder leaning against the wall. Oops. And it's a 50-foot ladder. Okay? Now, what's important about that right away is the assumption here is that the length of the ladder isn't going to change with respect to time. As the ladder falls, it's just going to slip out. So it's whatever length it is here, it's going to be the same length when it hits the ground. So that turns out that's a constant in this question. Now it is possible to have a ladder problem where that's not constant. Okay, now you might think of something called an extension ladder, okay, where the height changes. And actually you've probably seen stuff like that in all sorts of comedies. I mean, I can think of one right now where you see a guy climbing up the ladder, he's got it upside down, and the ladder collapses on him. Anyway, that's not what's happening here, but let's label this distance right here x, and this distance right here is y. Why not? And we can call the length of the ladder here z, but that's just going to be 50 anyway. So we know, what do we got here, that when the foot is 15 feet away, so when x is equal to 15, we're looking for the rate at which the top of the ladder is dropping. So we're looking for dy by dt. Don't know what that is, although I expect it's going to be negative. And I know that the wall, the foot of the ladder is moving out. It's moving out this way at 3 feet per second. So dx by dt, okay, is going to be 3 feet per second. And it's going to be positive because the value here, the distance that foot is away, is getting larger. I expect dy by dt to be negative because this distance here is going to get smaller as the foot slides out. Okay, I think that's everything we got here. So I'm trying to relate the three sides of the triangle here. I think it's pretty clear that the relationship I need is the Pythagorean theorem. So x squared plus y squared is going to equal z squared. Now I've warned people about this before. Please don't plug in values of the variable until after you take the derivative. And that is true, except in this case, z is not a variable. It turns out z is a constant. So I can plug that in right away. In fact, I want to. It makes the math a little bit easier. Because now when I take the derivative here, I'm going to get 2x dx by dt. Okay, and actually I know both of those values, plus 2y sorry, dy by dt, and it's going to equal 0. Okay, I don't even evaluate 50 squared because I know in just a couple seconds I was going to take the derivative. It was going to go away. Now, I am looking for dy by dt. So I'm going to isolate that. So dy by dt is going to equal, now, first of all, I should note that I can divide everything through here by 2. So the 2's are going to go away. But I'll bring that x dx term over, so that'll be negative x dx by dt. And there's that negative that I was expecting to pop out here. And then I would divide by the y. So I'm going to get dy by dt is going to equal negative x over y dx by dt. Wonderful. Now, I know what x is. Okay, x was 15. I know what dx by dt is. It's 3. Oh, and what I don't know is y. Okay, but that's okay because the situation that I've given myself here, I know what x is, and I know the length of the ladder. So all I got to do is to figure out what y is just use that Pythagorean theorem again. So in that specific moment that we're interested in, this is 15. Okay, and we know that the length of the ladder is 50. Okay, so 15 squared is just going to be 225. And 50 squared is going to be 2,500. And I bring that, whoops, sorry, that's y squared. So when I bring that over, I'm just making sure that I'm doing all the math right here. I've got my calculator here because I don't want to mess that up. I'm going to get that right there. And obviously I'm going to take the square root of that. Now, what I like my students to do, okay, and you have to figure out if your teacher wants this or not. I like my students to write the plus or minus there. Now, I recognize as well as they do that the negative doesn't make any difference here. But still, I like them to do that because I always want them to be aware that when you take a square root, you've always got this positive, negative option there, and then you got to choose. So, yeah, we're going to choose the positive one here. Now, I'm going to try to simplify that a little bit, but I think the only thing I can do here is yank out a repeated factor of 5, and I think that leaves me with 5 root 91. Which isn't a particularly great number, but anyway. So I'll plug that in over here. This becomes 5 root 91. Okay. And what do we got here? Well, not a whole lot here. The 15 divided by the 5 will be 3, so in the numerator I'm going to get negative 9 over root 91. And what's that going to be? That's going to be feet per second. Now that doesn't really give me much to I don't really know what that number is, so I'm going to actually convert that to a decimal. Just because if I convert to a decimal, it'll give me a far better idea of what's going on here. And that's going to be negative 0.94 feet per second. Okay, that means a lot more to me. Okay, that's nice because it's an exact form, but that actually means something to me. I mean, I get a sense of how fast 0.94 feet per second is. This one here, I really don't know. Now, there was a part B to this question. And part B was, at what rate is the slope of the ladder decreasing? Okay, well, now based on my diagram up here, remember, the slope of the ladder is, and slope is always rise over run, so in this case here, y over x. Okay, I know that my slope is going to equal y over x. So if I want to know how fast my slope is changing, now this question here, by the way, I think you have to assume, just the way it's written here, that all the other parts of this question are staying the same. Everything that was given to you in part A is intended to be used in part B here. But all I really want you to do is take the derivative of this. So dm by dt, and notice in this case here, I'm just going to use the quotient rule. I could have separated, sorry, I could have replaced y with, like I could have solved for y, made it, for example, a square root of 50 squared minus x squared. But because I already have, for example, I know what dy by dt is, I'm okay with this. So if I take the derivative here, the derivative of the numerator is going to be dy by dt multiplied by x minus y dx by dt all over x squared. See, I've got all the pieces. I know that dy by dt, for example, is negative 9 over root 91. I'm going to use this one because it is an exact form, not the decimal. I rounded to get that. Yeah, that was approximately negative 0.94. So I'll use the exact value. And I know that x in this particular moment here was 15. I know that y was equal to 5 root 91. And again, I'm going to use the exact value here. And dx by dt was positive 3. All over 15 squared. Now, even if I can simplify all this, okay, it's going to probably look a little weird here, so I'm just going to get the decimal value here. Whoops. Sorry. So I'm going to just go to my calculator here. Just take me two seconds to get this all entered. There's my numerator. Okay, and when I get everything said and done here, I get negative 0.70, sorry, not even units, per second. Oh, that looks terrible here, sorry. I'm going to write that again here. That's going to be negative 0.7 per second, because x and y here are both going to be in terms of feet, okay? And so those are going to cancel. And what we're going to be left with here is, actually, maybe even no, it'll be just negative 0.7 per second. That's how fast the slope of this thing is changing. Not a really common question, but you're going to see later on here how that might even link up with, wink, wink, nudge, nudge, some trigonometry. Alright, so in this related rates question, we read that the kite a girl is flying is 100 meters above the ground if it is being blown horizontally at a rate of 15 meters per second. Okay, well, so we've got a rate there. We've got to kind of draw this out here. So here's our scenario. So the kite a girl is flying is 100 meters above the ground. Okay, so 100 meters above the ground. So here's our kite. Okay, and then here's our girl right down here. It's being blown horizontally at a rate of 15 meters per second. So we've got to throw some variables down here. So let's say that this is x, this is y, and this is z. That's kind of that is just my personal kind of go-to for these things. You can use whatever variables you want there. But it's being blown horizontally at a rate of 15 meters per second. So basically that's going to be x changing here. So we know that dx by dt is going to equal 15 meters per second. The question is asking how fast is the string being paid out when it is 125 meters away from her. Now, that's the string is along z here, so we're being asked how fast is that changing, dz by dt. We don't know. That's what we're looking for when it is 125 meters away from her. Now, this question has caused in the past a bunch of confusion, merely because of a misunderstanding of what is meant by 125 meters away from her. I see a lot of students that believe that that's supposed to be along the horizontal line here, but actually, when you measure the distance that the kite is away from her, you're going to measure it directly to the kite. And so what we're interested in is how fast she's letting the string go when she's got 125 meters of string paid out. Okay? Now, we assume in this question that that kite stays 100 meters above ground. So it turns out this right here is a constant. So now the equation that we need that relates those three variables together will be x squared plus y squared equals z squared. We're going back to the Pythagorean Theorem, old favorite. It's just that this time now we can make this 100 squared equals z squared. And I'm going to take the derivative to get the rate of change. So 2x dx by dt. The derivative of 100 squared, doesn't even matter what 100 squared is, it's going to be 0. And then we get 2z, dz by dt. Okay? Now, I am looking for dz by dt, so I'm going to bring the 2z over. Now the 2's will cancel, and we get x over z dx by dt is going to equal dz by dt. Okay. Now, this is a pretty standard sort of a situation here. We know, in this particular case, that dx by dt is going to be 15, positive 15. We also know that z is 125, so we know that this is going to be over 125, and then this is going to be multiplied by 15. But again, and we've seen this before, what we don't know is one of the sides of the triangle at that particular point here. But that's okay, because we have the Pythagorean Theorem. So if I just come over here, and I'm going to enter in what we know. We don't know x, that's what we're looking for. Okay, but we've got 100 squared. And then we know at that particular moment that we're interested in that the length of z is 125 squared. Okay, well, 100 squared is going to be 10,000. 125 squared is 15,625. Okay, and so now all I got to do is move that 10,000 over. We get that x squared is equal to 5625. Okay, and I'm going to simplify that. Now, ideally, it would be wonderful if that was a perfect square, and I doubt. I'm just going to check. Oh, it is a perfect square. That's wonderful. So, when you take the square root of both sides here, now again, I've mentioned this before, with my students here, I really do appreciate it when they write the plus or minus there, and then I like to see them negating the negative here because it doesn't make any sense. So 75 meters. So now when I bring that 75 meters over, we can finish the problem. I can put that up top here. And so then you've got 75 times 15 divided by 125, and it turns out that works out to a nice beautiful 9 equals dz by dt. Whoops. Now, let's be aware though, we've got the units here. That's got to be 9 meters per second is dz by dt. So she's really letting out the string really quite fast to let that kite go, being blown away at 15 meters per second. Right now in this question we read that water flows through a large funnel, okay, that is in the shape of an inverted cone. Yeah, so another cone question. It enters the funnel at 0.5 meters cubed per minute. Okay, so we know, okay, this looks like a change in volume. So dV by dt is going to equal 0.5 meters cubed per minute. The funnel is 4 meters tall. Okay, now we got some dimensions on the tunnel. 4 meters tall and has a radius at the top of 3 meters. Okay, so let's maybe look over here. So here's, whoops. My pen's starting to dry out here. Okay, so here's our funnel here. We know that's got a height of 4 meters, and the radius at the top there, the radius is 3 meters. Okay, when the water is 1.5 meters deep, so we're going to have the depth of the water, the height of the water, 1.5 meters deep, the water is increasing at a rate of 5 centimeters per minute. Okay, well now that's interesting. Okay, so now we've got the dH by dt here. Now normally with these questions, that's what we're looking for. So this is a little bit of a different take on this particular question. Now, one thing you really should notice here is that everything has been in terms of meters except for right here. And so we need to change that. Now, the time units have been the same, but that is different there. So I got to convert that to a meter there. So it's going to be 0.05 meters per minute. Now, that is an interesting scenario here. So we got to keep reading here to figure out what's going on here. How fast is the water exiting the funnel? Oh, okay. So here we go. So we're putting a water in, and that's what the dV, the initial dV by dt is. So this is our in, maybe, and then we're going to have volume out here. Okay, so we got dVi by dt, the rate at which it's going in and the rate at which it's going out here. Now what we're interested in is the rate at which it's exiting. Okay. Now the volume. Okay, the volume of this thing is going to be related to the volume in and the volume out. So this is adding volume, this is subtracting volume. So really what we've got here is we got to figure out just how volume is changing here. Okay, I already know how it's being added to. I want to figure out what's being subtracted here. So what we're going to do here is just look at how volume relates to the different variables here. So pi r squared h. Now the nice thing is we know that at any particular moment, here's the radius, here's the height, we've got a ratio here that the radius and the height follow here. So for the whole cone, height to radius is 4/3. So that means that any volume of water that fills up the bottom of that funnel there is going to also have that same ratio there, height to radius. Now in most of these cases here we're going to solve for r, and this one's no different. So r is going to equal 3h over 4. And the reason for that is because we've been given dH by dt, and we've been given the height. So we kind of want that variable to stay in the problem. So now I come over here. This is going to be pi 3h over 4 squared h. And so putting that all together, that's going to become 9 pi h cubed over 16. There's my volume. Okay, good. Now I've got a relationship between volume and height of the water there. dV by dt, dV by dt is going to equal, bring down the 3, it's going to be 27 pi h squared over 16 multiplied by dH by dt. Now, I know all of that. 27 pi, we knew that the height was 1.5. That's going to be squared over 16, and we know that dH by dt was 0.05. Okay, so that's the rate at which the volume is changing. And let's get a decimal value for that. That's probably going to make that a little bit easier for me to work with. So 27 times pi times 1.5 squared times 0.05, and that's all divided by 16. And so we're going to get 0.60 really meters cubed per minute. Now, I'm going to leave that decimal on my calculator, okay, so you can see that. I'm going to leave the full decimal on my calculator. Now, volume, the volume of this cone here is going to be the volume in minus the volume out, which means my volume out is going to be the volume in minus the change in volume. So dV out by dt is going to equal dVi by dt minus the change in volume overall by dt. Now, I know both of these pieces. I know that we are pumping water in at 0.5 meters cubed per minute, and I know that we are losing it at 0.60 meters cubed per minute. So on my calculator, 0.5 minus the answer that I came up with just previously, and we get here that we are actually losing at 0. Well, okay, to the nearest hundredth is going to be 10 meter cubed per minute. Okay, which makes sense. That's actually consistent. I didn't have to leave that in there, but that's okay. It worked out the same way here. So yeah, what's going on here is the water is exiting faster than we're putting it in. Perfect. Okay. So in this related rate question, we read that square ABCD 30 centimeters on a side. Okay, let's just start drawing that. Okay. Whoa. Okay, here we go. So A, B, C, D. And it's 30 centimeters on a side, so 30 centimeters. That's going to be the same on all four sides there. An ant is observed crawling along the side of the square from point A to point B. So we got this ant crawling this way at 1 centimeter per second. Okay, so I tell you what, let's keep reading here. Just got to figure out what the question's asking. How quickly is the distance between the ant and point C? Okay, that's what I needed. So here's my ant, and we're interested in the rate at which the distance between the ant and point C is changing when the ant is halfway to point B. Okay, so let's call this distance right here, let's call that X. We'll call this Y, and as I've done a few times before, we'll call this Z. So we know that dx by dt, we know that the ant is crawling at 1 centimeter per second, so this distance here is getting smaller at 1 centimeter per second, so negative 1 centimeter per second. We know that all of the sides here are 30 centimeters in length. Okay, so in this case right here, notice that in this triangle that we've drawn here, y isn't going to change. So y is actually going to stay 30 centimeters. That's going to be a constant in this question. We are looking for dz by dt. Don't know what that is, but we do know that the point that we're looking for, or the moment that we're interested in, is when the ant is halfway. And so in other words, when x is going to be equal to 15 centimeters. Okay, now when you look at this, it should ring a bell. Looks like a Pythagorean Theorem question. And isn't it interesting how many of these end up being Pythagorean Theorem questions? So x squared plus y squared is equal to z squared. Again, I can, because y never changes, okay, I can plug in 30 immediately. And so when I take the derivative, 2x dx by dt is going to equal 2z dz by dt. Because the derivative of 30 is 0, it goes away. I am looking for dz by dt, so I will divide by 2z. The 2's will cancel, so x over z dx by dt is equal to dz by dt. Okay, good. Now, I know that x is 15. I know that dx by dt is going to be negative 1. And as with so many other questions like this that we've done, it's that final side that I don't know. But that's okay. I've got the Pythagorean Theorem. So I know that x is 15. I know that y is 30. I just don't know what z is. So 15 squared is 225. Oops. 30 squared is going to be 900, is equal to z squared. So put those together and we get 1125 is equal to z squared. Now I'm going to take the square root of both sides. And again, I really like seeing that plus or minus just so that everybody knows that belongs there. But again, because of the scenario here, the negative one doesn't make any sense. Now I'm going to see if we can simplify this a little bit. And yeah, I can pull out I can pull out a pair of 5s out of there. I can also pull out a pair of 3s. And so this is actually going to become 15 root 5, it looks like, when I simplify that. And I'm just going to double check that by just... Yeah, that's true. So 15 root 5 there. Perfect. So I come over here, I get 15 root 5. Well, I can see right away the 15's cancel. This actually reduces down to a beautiful negative 1 over root 5 equals dz by dt. Except for the one thing that doesn't actually communicate a value to me that I can get my head wrapped around. So I'm going to just create the decimal value here. So dz by dt is going to be negative 0.4 centimeters per second. Now that's approximately how fast dz by dt is changing. Okay, and there you go.